It's our pleasure to have Rob Morris as a speaker in our seminar. He needs no introduction in a sense, but I'll still say a couple of words. He's a great expert in extremal combinatorics, and he is in Rio. I hope he'll share some of the sunny weather with us by giving this talk. He gave a lecture at International Congress of Mathematicians, the last one that happened in Rio, and was a student of Bela Bolobash. So, thanks for agreeing to give a talk. And, please, welcome.
Okay. Thanks very much, Andrei. It's a great pleasure to be with you. I've never been to Moscow in person, so this is the closest I've been so far. Okay, so I'm going to tell you about a thing called Erdős covering systems, and I won't assume that you know anything about them at all. But I should first mention my amazing co-authors. I'm very lucky to get to work with them. Paul Ballister, who then of Memphis, now of Oxford, Bela Bolobash, who you all know, of Memphis and Cambridge. Julian Sazrabude, who is in Cambridge, and Marius Tiber, who's a student of Bela also in Cambridge. And Marius will be on the job market soon, I believe. So everyone who's looking for excellent postdocs. Right, what is a covering system? So what's a covering system? It's just a finite collection of infinite arithmetic progressions whose union is the integers. Right, so this looks like a sort of number theoretic or additive combinatorics object, but we'll see that it quickly turns into a sort of more sort of geometric combinatorial object pretty soon. So these were introduced by Erdős in 1950. I'm going to start with, I was asked to start by giving some history, so I'm going to spend the first sort of 20 minutes talking about some of the early history of these and the motivation for these objects, which is mostly number theoretic. So I'm just interested in covering systems with distinct moduli. So obviously it's easy to construct a covering system. Just take, say, the evens and the odds, or take, 0 mod 3, 1 mod 3, and 2 mod 3, and you cover everything. So it gets a bit more interesting if you restrict yourself so that all of the moduli, that is the common differences, have to be distinct. It's not completely trivial to come up with an example. Here is perhaps the simplest one. And I want to spend just a couple of minutes thinking about this one, just to get our heads into how to think about these objects. So how do you see that this is a covering system? Well, it's good to think about it geometrically in the following way. So I've written, we're working mod 12, so the least common multiple of these moduli is 12. So everything is in Z12. And I've written out Z12 as Z4 cross Z3. So the columns you see are 0, 1, 2, and 3 mod 4. And the rows are 0, 1, 2 mod 3. Okay, so what does the arithmetic progression 0 mod 2 look like? It just looks like the even, so 0 and 2 mod 4. So it's a rectangle. Okay, this is always going to be the case. Okay, so you knock out all the even numbers, you knock out those two columns. What does 0 mod 3 look like? This is the bottom row. So that knocks out that. What does 1 mod 4 look like? It's the second column. That knocks that out. What's 5 mod 6? Well, it's 11, but not 7. And what is 7 mod 12? It's the last one. Okay. So the way we formed this covering system was we sort of took out some big chunks at first, and then we sort of filled in the details by hitting the last ones. Okay. So I hope that's fairly clear. So I just want to note before going to the next slide, note that we use mod 6 here. That will be important on the next slide. Okay. So here is the original application. The reason Erdős introduced these in 1950 was to prove the following theorem, which answered a question of Romanov and apparently refuted a conjecture of de Polignac. It says the following: not all odd numbers are of the form 2 to the k plus p, with p being a prime or 1. This was conjectured and asked by some well-known people. And Edge gave the following, I mean, really stunningly beautiful proof. So I just want to tell you how the proof goes. So, use the following observation, that this collection of 6 arithmetic progressions is a covering system, which you can check the same way we just did on the previous slide, right out to sort of Z24 and observe that you hit everything. Okay, so why is this useful? Well, k, in the 2 to the k, has to be in one of these sets. So let's look at them. First, suppose k is 0 mod 2, then 2 to the k is 1 mod 3, right? Because 2 to the 2 is 4, which is 1 mod 3. Okay, so if x is also 1 mod, I should say 3, sorry, that's a typo. If x is 1 mod 3, then 3 divides x minus 2 to the k. Sorry about that. Similarly, for the next one, if k is 0 mod 3, then it is 2 to the k, well, 2 to the 3 is 8, which is 1 mod 7. So 2 to the k is always the same thing mod 7. If k is 0 mod 3, then 2 to the k is always 1 mod 7. So 7 also divides x minus 2 to the k. Next one, if k is 1 mod 4, well, 2 to the 4 is 16, which is 1 mod 5. So if k is 1 mod 4, then it's always 2 mod 5. 2 to the k is always 2 mod 5. So 5 divides x minus 2 to the k. You can do this for all the others. The reason this always works is because there is a classical theorem that says if n is not 6, then there's always a prime that divides 2 to the n minus 1, which does not divide 2 to the m minus 1 for any m less than n. So so you can always find a new prime to do this with. And it's because you don't have 6, because none numbers are 6. So what does this tell you? So you continue for all 6 cases, and you obtain an arithmetic progression that is all the x's that satisfy these 6 congruences. So by whatever it is, Chinese remainder theorem, whatever, you can find a solution of x. And for any such x in this arithmetic progression, and any k, one of these 6 primes divides x minus 2 to the k. So this p would have to be either 1 or one of these 6 primes if you take these particular x's. But how many numbers are of the form 2 to the k plus p, where p is one of 7 primes? Not very many. So there's no way you're going to fill out a whole arithmetic progression like that. So this sort of stunningly simple and beautiful proof by Erdős, this was the original motivation for the study of these objects. Okay, so immediately after giving this proof, Erdős stated in this same 1950 paper the following problem, which would become one of his most famous and one of his favorite open problems, which is as follows. So do there exist covering systems of arithmetic progressions with distinct moduli with arbitrarily large minimum modulus? So all of the moduli, all the common differences, arbitrarily large. So he observed that you can avoid 2. So already avoiding 2 sort of takes a bit of thought, and commented that it seems likely that you can do this, just he couldn't see how to do it. And it seemed like throughout his life he was confident that these things could be constructed, just we were being blind, or we didn't have the tools to do it. But he noted that this would have the same proof would, if this were true, then the same proof would give this this nice number theoretic application. Okay, so we're going to come back and talk about this this minimum modulus problem in great detail later. So I won't say anything else about it right now. Okay, here's another old problem and some more motivation. So Erdős asked this in 1965, and then conjectured that it's true. That there exists a covering system with all moduli distinct and odd. So not only you avoid 2, but you avoid all even numbers. And in fact, he conjectured at some point that you can even avoid all small prime factors. So arbitrarily many small prime factors. So Selfridge was also interested in these questions, and he thought the opposite was true. So this has become known as the Erdős-Selfridge problem. So this also has some sort of motivation, algebraic motivation this time. So Schinzel discovered that if the answer is no, if no such covering system exists, then certain class of polynomials, of every polynomial with these few conditions, then there is an infinite arithmetic progression such that x to the n plus f of x is irreducible over the rationals. Okay, so I mean, perhaps it's not so exciting for people in combinatorics, but it's not, these things are interesting to people in other areas. Okay, and he also showed that if this is true, then it would imply another nice property of covering systems. In any covering system, one of the moduli divides another. Okay, so the Erdős-Selfridge problem, if the answer is no, it implies a thing about polynomials, which in turn would imply this weaker conjecture of Schinzel. Right. We'll see. So I'll return to this later on as well. So this we'll see that Schinzel conjecture really is sort of weak. So it's really weaker than the Erdős-Selfridge problem. Okay. Okay. So not much progress was made on any of these problems. So in 1980, Erdős and Graham suggested a slightly different direction, which turned out to be, in some sense, the key to getting into the problem. So this was a very good question to ask. They said, okay, maybe we could also be interested in the density of the uncovered sets. Let's not just show that you can't cover. Let's show that actually you must miss some positive proportion. They conjectured that if you're in the interval n up to constant times n, then you should miss at least a positive proportion of the world. Okay, and this was proved by Philosetta, Ford, Conjugating, Pomerantz, and Yu in the following sense. So I'd like to spend just a couple of minutes thinking about this statement. So this paper was extremely important in basically breaking open this problem. It had been totally stuck for more than 50 years. This paper really kind of got the area going. So what did they prove? They proved that, okay, in this setting, if you're working in n up to constant times n has to be, super polynomial in C, but not crazily large. Then, if you have distinct moduli, then the uncovered set not only has positive density, it has basically as big density as you could possibly hope for. So what is this 1 minus 1 over d? Well, 1 over d is the density of the arithmetic progression with difference d. So that's how much you knock out with one arithmetic progression. If you just throw them in randomly, so throw in your arithmetic progressions randomly, you'll knock out basically this much. Right? What they're saying is that if your moduli are pretty large, like and so not too far apart, then you basically can't do better than random. So no matter what you do, your arithmetic progressions are sort of orthogonal to each other. Right? You just knock out a random proportion, basically whatever you do, or actually whatever you do. Okay? So this sort of strongly hints that probabilistic combinatorics should be involved, and in fact, their proof used a key lemma in their proof was essentially a variant of the Lovász local lemma. So this is the first paper that really connects this apparently number theoretic problem to probabilistic combinatorics. This is a very important breakthrough. Okay. Okay, so this is the theorem again. They're also motivated by this theorem. So they proved another theorem as well, which I'll state a little later. They're motivated by this to ask the following beautiful question, which is one of the questions that got us interested in these problems. So given the intuition above, given the theorem above, it sort of suggests that perhaps if the sum of 1 over d is bounded, right, and all of the moduli are large, perhaps the arithmetic progressions act as if they're sort of independent of each other, sort of orthogonal to each other. In which case, you might hope that how much survives maybe as much as e to the minus c. Right? If you just doing this thing randomly and they're all large, then about e to the minus c would survive. They said they couldn't decide whether they thought it was true or not, that a positive proportion should survive in this setting. So we'll later on see an answer to this question. So this is a really lovely question, I think. Is there any questions at this point? Is everyone happy?
I actually wanted to ask you to return to this proof of Erdős.
Yeah, sure.
It for a second because I think I missed some. So can you maybe summarize it in a couple of words again?
Right. So K is in one of these 6 sets, whatever K is, and for each of them we can find a congruence. So this X is congruent to a 1 mod 7, for example, using a different prime in each case, such that if X satisfies that congruence, then you get some divisibility condition. Let's look at all of the X's that satisfy all of these 6 congruences. And because the 6 primes are different, there will be such an X. In fact, the whole arithmetic progression of such X's.
Yeah. Okay.
So for such an X, for an X in this arithmetic progression, any K, one of these 6 divisibility conditions must hold. Right?
Yeah.
So let's look at those X's.
Yeah.
Right. Well, if right, so this P in 2 to the K plus P, this is right, if that equals X, if that's then P is now X minus 2 to the K. So one of these 6 primes divides P. But P is prime. So P is one of these 6 primes. But that doesn't leave many options, right? You've only got numbers of the form 2 to the K, those sort of extremely sparse, and 6 primes that you're allowed to. Right, so there's no way you can fill out that whole arithmetic progression.
Oh, okay. Great, but how does one use this covering system? So this is the choice for K, right?
The covering system is for K, exactly. So there's only a finite number of choices for options for K.
Okay.
And I think it's very surprising.
Yeah, it is very surprising.
Right. Okay. Okay. So where are we? Okay. So just to summarize where we've been so far. So we're motivated by the following questions in particular. So the minimum modulus problem. So do there exist these covering systems with arbitrarily large minimum modulus? We also got interested in this question of Erdős. So she discovered it was asked by Erdős somewhat after starting to think about it, because Bela found this paper in Hungarian from 1952, which it turned out was the first paper that Erdős had given him to read when he was a teenager. And he'd forgotten about it until we started working on it, when he remembered. Anyway, so in this paper in Hungarian, he asks, I am reliably informed, how many minimal covering systems of size n are there? And I'll talk about this in just a few minutes, or in plus 1 minute. Right, and also this beautiful question of Hiloseta, Ford, Konjagin, Pomerance, and Yu about the density of the uncovered set. Okay, so we're interested in these 3 questions. Right. And other questions as well, but these perhaps for me the main ones, the most exciting ones. Okay, so I'm going to start with this this counting problem, partly because I think it gets us into thinking about what these covering systems look like. So Erdős in this 1952 paper gave a very simple proof, just a few lines. There are only finitely many of them. So basically, it showed that you can bound the size if you order the common differences, then the kth is bounded by some function of the first k minus 1. So it gives finitely many. If you work it out, then you get something like 2 to the 2 to the n. Okay. So just a comment: why do we have minimal in the question? Well, if you don't have minimal, then the question is silly, because you can just cover, and then you can add in anything you like. So there are obviously infinitely many, even of size 2. Just cover with z and then take a to be anything. Okay, so minimal is a sensible condition to put on it. Okay. So there was improvement in 1985 by Simpson, who proved a lovely extremal result. So he basically gave an extremal result in terms of the least common multiple of the common differences, the moduli. In particular, implies the largest modulus in a minimal covering system of size n is at most 2 to the n minus 1. And there's a very simple example that shows it's sharp. So if you take, so this will be important in the next slide. So perhaps I'll go through it slowly. It's very simple. So you take 1 mod 2, then you're only left with the evens. If you then add 2 mod 4, you're only left with 0 mod 4. And if you take 4 mod 8, you're only left with 0 mod 8. Continue, and then finally fill in the 0 mod 2 to the whatever, 2 to the n minus 1. Okay. Okay, this is about the simplest example of what we're going to call a frame. These frames play an important role in the proof. And note that if the largest modulus is of size most 2 to the n, and there's n of them, then there are most 2 to the big O n squared of them, right? Because they're just 2 to the n choose n. Okay, this is an improvement on Erdős is bound.
Sorry, Rob. So what was the Erdős bound on this dependence of the? Is it easy to state?
It's like 2 to the n. So he showed that the kth one is at most something like the least common multiple of the first k minus 1.
Okay.
Doubly exponential.
Doubly exponential. Yeah. Right. Okay. So this was the frame we just mentioned. Covering system we just mentioned. So I say we. So I think this is I guess Simpson's construction, but so let's generalize this construction as follows. Okay, so let's look at the first k primes. Look at their product. So throughout, I'm going to use qk for this some sort of product of sets or product of primes or whatever. Sorry, it won't always be the product of the first k primes, but we'll see. Right. And we're going to do the following. So this looks slightly confusing, but on the next slide, I'll give a gentle explanation. So for each prime and for each a, so 1 up to p minus 1, we're going to choose an arithmetic progression to knock out basically a mod pi. But we're going to do it because in the previous rounds, we'll have knocked out everything except 0 mod qi minus 1. We'll multiply, make sure we're also a multiple of qi minus 1. Okay, so I claim that together with 0 mod qk, these cover everything. So I suspect this is not obvious, but hopefully after the next slide, when we do a gentle example, it will become obvious. Okay. Okay, and I'm going to call such a thing a frame. Okay, so the idea is for each prime, we knock out everything except 0 mod that prime. And then we continue to the next prime, knock out everything except 0 mod that prime, and so on. Oops.
And this d dividing qi minus 1.
Right. So this is our this gives us lots of choice. So any d works, and we are free to choose which d we use. And this is going to give us lots of choice, lots of covering systems.
Okay.
So, right, so this is just a repeat of the definition. Okay, so for example, so if p is 2, then let's take, we have to take 1 mod 2. There's no choice. Okay, so we're left with the evens. Now, for p equals 3, we could take, we're going to knock out 1 mod 3 and 2 mod 3, remembering that we're working in the evens now. So if we we can knock out 1 mod 3 and 2 mod 6, say. Because now we're using the primes 2 and 3, so we are free to use 3 and 6. Okay, or we could take 2 mod 3 and 4 mod 6. In both ways, we've knocked out 1 and 2 mod 3 in the evens. So meaning 2 and 4 mod 6. Okay, so we have 2 choices here for p equals 3. So we're left now with 0 mod 6. Okay, for p equals 5, then we have to knock out 1, 2, 3, and 4 mod 5. We can do it with any choice of the ones we have. We have 5, 10, 15, and 30. We can choose which one takes out which one. Okay, this is an example that knocks out 1, 2, 3, and 4 mod 5 with 4 different moduli. And we're left with 0 mod 30 now. Equals 7, we want to knock out 1, 2, 3, 4, 5, and 6. We have a bunch of different Ds we can do it with. So here's just an example of what we could do. So this knocks out, yeah, I can't even see what it does, but anyway, 2, 4, 1, yeah. Anyway, this knocks out. So now after this, we're left with only 0 mod 2 to the 10. And eventually when we want to finish, we just stick in 0 mod qi or qk, whatever, the last one. Okay. So if you think about it, then this is just a convenient way of writing. The thing at the top is a convenient way of writing what we've done.
And you always want D to be distinct, or?
So thank you. Good question. For this problem, it doesn't really matter. So I'm giving an example where they're distinct to show that we can do it, but it won't actually affect the counting very much. So it's that will be a lower order term. But yeah, thanks. So that's I should have said. That's a good question. Yeah. So at the very beginning, when the primes are small, then you have to try to make sure you don't take the same one twice. Later on, when the primes get much bigger, there's so much space that it's easy to avoid hitting the same one. Is like 2, right? So when we're knocking out the prime pi, we have to, so that when we're knocking out the ith, we're dealing with the ith prime, we have pi minus 1 progressions to choose to knock out 1, 2, 3 up to pi minus 1. And how many choices for d do we have? We have 2 to the I minus 1. Okay, so we're just choosing like pi things from 2 to the I things. Okay, so here's do the counting. If you do the counting, then you get roughly this many frames. So why is that? Well, how large is each frame? So for each prime pi, you have to choose pi minus 1 arithmetic progressions to knock out 1, 2, 3 up to pi minus 1. And then 1 at the end to fill in the 0 at the end. Well, pi is roughly I log I. So this sum is basically k squared log k, up to a constant factor. Right? Okay. So that's how large the frame is, if you use the first k primes. How many choices do we have? Well, we get to choose for any fixed I and A, we get to choose D. And D can be any divisor of qi minus 1. So there are 2 to the I minus 1 choices. Right? Because qi minus 1 is p1 times p2 times p3 dot 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 times pi minus 1. Okay? You just choose which of the primes you're taking. So what does this give? This gives the product over I of 2 to the I minus 1 choices for each D, and we use pi minus 1 Ds for the prime pi. We have that many different frames. Well, pi is roughly I log I, so this is basically e to the k cubed log k, and n is k squared log k, so that's like e to the n to the 3 over 2 over root log n. So very simple counting gives us lots and lots and lots of covering systems. Okay, it's just counting these frames, which are these relatively simple objects. So these frames, I should emphasize, these are the things that Simpson showed are extremal for a covering system with a given least common multiple of its moduli. So if you fix the least common multiple of the moduli, the smallest covering system is given by a frame. Okay, so this is so we got a lower bound of like e3 over 2. We have an upper bound of e to the n squared, which you think is the right answer. So it turns out that the lower bound is the right answer. And we can also get the constant in front, which is this funny, involves this funny tau, sort of sum of log 1 plus 1 over t squared, which apparently this constant we were told afterwards appears in other contexts. And can I find this? Yeah, Christian Elschotz kindly observed that this also appears in the iterated divisor function. But it's not really clear, at least to me, what the connection is, if any. Okay, so this is rather nice. And the proof, as you might imagine, involves studying the rough typical structure of a minimal covering system. So more precisely, what we think is that all covering systems should sort of, in some sense, would be sort of look like be in an approximate frame. So we're not able to prove that. We don't have a theorem of that form, but we show in a sort of certain weak sense that it's true. So it's a weak enough sense that the proof works, and a strong enough sense that we can count. So slightly more precisely, so the way we do this is to show that an efficient minimal covering system. So remember again, Simpson showed that the extremal covering systems are frames. We showed if you're within a constant factor of Simpson's bound, your size is within a constant factor of Simpson's bound, we say you're efficient. And in that case, you contain a very large approximate frame. So I don't want to define an approximate frame because it's a bit technical, but you just think of it being a frame you kind of mess around with a little bit. So start with a frame and then sort of jiggle a few things, jiggle a sort of little o1 proportion of them. And large means basically 1 minus little o1 times what you could hope for. Okay, so you find a sort
efficiency. How do you measure the efficiency?
Yes, so efficient means that your size is within a constant factor of Simpson's lower bound. Simpson's lower bound is saying fix the least common multiple of the moduli, then the best thing to do is to take a frame with that least common multiple. If given your least common multiple, you're within a constant factor of that in your size, then we have this structure. If you're out by more than a constant factor, you can count fairly easily. So there are very few that fail this efficient condition. And the ones that are efficient, we can find this sort of reasonably strong structural statement. Okay, and this in sort of the popular language is a sort of inverse theorem for Simpson's theorem. So if you're or a stability theorem, if you're anywhere near the extremal bound, then you have some kind of structure. So a stronger version of this should be true, but the version that sort of came out of our argument was enough to do this counting. So I think this more precise structural theorem or more precise structural conjecture, it would be very interesting to do this. There's a chance that one could do it by taking our method and sort of using a bunch more power. It's not really clear to me there's a definite obstruction, but it would definitely require quite a bit of work. The proof of this is already quite complicated, so I'm not going to tell you anything more about this proof because it's quite technical. I probably need at least an hour and a blackboard to give any idea. I'm going to tell you instead about a much sort of simpler and cleaner and prettier proof. Okay. So I want to take a break soon, but perhaps I'll just set up the minimum modulus problem, and then we can maybe take a 5-minute break. So recall this this very famous question of Erdős: do they exist these covering systems with an arbitrary large minimum modulus? So Erdős managed to avoid 2, and several people have managed to avoid 3. And then some years later, Churchhouse managed to get all the way up to 9. It's already something of an achievement. Krukenberg jumped up to 18 years later, and then 20. So it's going up gradually. 24, it's still sort of only every 10 years or so. And then 25, that one took quite a long time. 24 to 25 took, 25 years. And then Nielsen really tried to sort of systematically do this in this 2009 paper. And he came up with these unbelievably complicated constructions with minimum modulus 40. And he at the end of this, he basically suggested that perhaps it's just not possible, that he'd tried in a very systematic way, and it really seemed that it was sort of, it was not, you're not going to get much beyond this this 40. The current record belongs to his student Owens, who modified his method and got 42. Okay. So in the other direction, so I already mentioned this beautiful paper of Philoceta, Ford, Connigan, Pomerance, and Yu. So as well as proving this conjecture of Erdős and Graham, they also proved a conjecture of Erdős and Selfridge, which is the following. So if the moduli are distinct and sufficiently large, then the sum of the reciprocals of the moduli should tend to infinity with m. So this is the bound that they got. The point is really just that the right-hand side tends to infinity as m tends to infinity. Okay, this is a conjecture of Erdős and Selfridge, so an attempt to weaken the minimum modulus problem. And again, it was a very good question because this led in a very interesting direction. So again, this is the method of these 5 authors introduced probabilistic combinatorics to the area, and in hindsight, their method was a one-step version of what Hoff did in 2015. He resolved this minimum modulus problem. He showed that, okay, it really is difficult to construct these things because they don't exist. So in this this wonderful theorem of Hoff says that the minimum modulus really is bounded. It's a most 10 to the 16. Okay. Right, and so I'm going to give just finish this slide. So I'll first give a very rough sketch of the proof, and then I'll spend the next half an hour giving a much more detailed sketch of the proof. Okay, so this is a preview of the next half hour of the talk. So here's the idea. You reveal the arithmetic progressions not one by one, but prime by prime. And you try to track the evolution of the uncovered set. So what does that mean? So Hoff's perhaps most brilliant idea was this: you should define a probability measure that distorts the space. And what do you want this probability measure to do? You want it to make the uncovered set bigger. We'd like to do it without, I mean, you could just make the uncovered set 1, but you don't want to, right? You don't want to do something so crude. You want to do something sort of a little more subtle. So hopefully without distorting the measure too much. You want to sort of blow up the uncovered set, but still keep the measure looking sort of uniform-like. And in fact, so his measures ended up being sort of quasi-random in a certain sense. Right, so you try to bound the distorted measure of the set that you cover in each step. So he used some complicated quasi-randomness condition to show that basically the distorted measure that you cover in each step is roughly what you get if you did it randomly. So you can't do much better than random in the distorted measure in any single step. Right, and if you do this, then you can show that you don't remove more than you would in the random case. And in the random case, you don't cover everything. Right, in the random case, you just cover a random 1 over d proportion. So you're left with this product of 1 minus 1 over d. Okay, so that's a very rough sketch that won't make very much sense, but okay. After the break, I'll give a simpler version of this proof, which hopefully you can basically understand the whole proof in sort of 20, 30 minutes. Right, so let's take a 5-minute break, and if anyone wants to ask questions, then please go ahead.
Rob, is the Hugh proof similar to the Pomerance, Connigan, and others proof?
Yeah, so good question. So Hoff was inspired by their method. He says so in his paper. So they do everything in one go, and Hoff does things in chunks. Mm-hmm. So we will do things prime by prime. Hoff divided into sort of a bounded number of chunks of primes. So their method can be sort of, it looks a bit like, it's not the same thing, but it looks a bit like one step of Hoff's method.
Okay.
So Hoff broke into this bounded number of chunks, and because of that, everything got more complicated, and so he had to do a bunch of other stuff with quasi-randomness, which is extremely clever and quite difficult to understand. So I still don't really feel like I am totally on top of Hoff's proof, but fortunately the proof I'll present is much simpler. It uses the same ideas, but with a sort of a twist, and it makes life much simpler. But yeah, all of this really should, so these are the Philosetta Ford conjugating Pomerantz U paper was a really big breakthrough that Hoff then sort of built on with a bunch of extra really clever ideas. And then what we did was really just a refinement of what Hoff did. But what I think we're left with after this sort of this simplification, this refinement. So this Hoff paper, I don't think people really, people know of it, but my impression is that very few people have read it. Very few people know the technique, and many people seem to think, okay, that just ends the subject and there's nothing else to say. But in fact, it seems to me that the method I'm going to present is very flexible. It should have lots of applications in other combinatorial problems. I feel like I'm not really equipped to find those applications, but it seems to me that the people who have a good eye for sort of remembering problems and spotting where you might use a technique might be able to use it in various other places. It seems both very powerful and very flexible. So I'm hoping that if I keep talking about this to enough people, then someone will take it on and prove a bunch of other stuff with it.
Sounds exciting.
Yeah, I've been attempting and failing to apply it in other places.
But does the simplification improve the constant?
It does as well, yeah. So it gets down to less than a million.
Less than?
Less than a million, so something like 600,000.
Really good.
That takes quite a bit of extra work. So the version I'm going to tell you would prove a much worse constant. Would be sort of, I don't know, 2 to the 100 or something. But the proof is then very simple. Okay, so
I think we can go on with it. Yeah.
Yeah. Okay. So in order to talk about things in sort of a nicer way, we're gonna translate into this more combinatorial or geometric setting. So this S1 to Sn, you should think of as being the primes. So Si is 1 up to Pi or something. And we're going to be interested in this this product of these sets. So we're working in this this high dimensional cube, high dimensional cuboid. Qn and the Qk is just the partial. There's what you get from the first k of these things. Okay. So we're now in this nice combinatorial setting, and we're working with hyperplanes, which are for us going to be axis parallel. So each yi is either the whole world or just a singleton. Okay, so we have these very simple hyperplanes. Okay, so they're all sort of parallel to the axes. And these hyperplanes correspond to the arithmetic progressions, and the Qn corresponds to the integers Zn, but using the Chinese remainder theorem to write them as Zp1 cross Zp2 cross ... Okay, and for simplicity, we're going to work in the square-free world. So I'm just going to assume that you only use each prime once. It doesn't really make a big difference, but it makes everything, all the calculations, just a bit prettier. Okay. Right. So what does the modulus of the arithmetic progression correspond to? It corresponds to the set of fixed coordinates. So if a coordinate is fixed, that's equivalent to the prime divides the common difference. Right? So each SI corresponds to a prime, and each fixed coordinate corresponds to a prime that divides the modulus of the arithmetic progression. And the hyperplane is the arithmetic progression. Okay, so the shift of the hyperplane corresponds to the shift of the arithmetic progression. The dimension or whatever of the hyperplane tells you the common difference. Okay, and we're going to say that two hyperplanes are parallel if they're the same fixed set, which is the same thing as they have the same common difference, the same modulus. So if we're looking at covering systems with distinct moduli, that's going to be the same thing as non-parallel hyperplanes. Okay, so we just translated into this world of hyperplanes where everything is a bit more combinatorial and geometric. Okay, so I'll try to remind you of these things a bit later. So I hope that this is fairly clear. So so that the translation is just the Chinese remainder theorem. Perhaps it's not even worth really worrying about it. We're in some nice geometric setting now. So there's an essentially equivalent geometric setting. We have this high dimensional cuboid. I'm interested in non-parallel families of hyperplanes. Okay. Right, so this is just a reminder of the definition. Okay, so we're interested in non-parallel families of non-parallel hyperplanes. We want to cover the whole of this Qn being this this S1 cross dot 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 cross Sn. Okay. And here's the theorem that we're going to prove. So, right, if the sets are growing linearly with some reasonable constant, then there's a constant C such that for any collection of hyperplanes that cover the whole space, so remember that's hyperplanes are like arithmetic progressions, and so this is like a covering system. Either two are parallel, so if no two are parallel, so if the moduli are all distinct, then there's a hyperplane whose fixed set is in the first C coordinates. So that means only the first C primes are allowed to divide the common difference. So therefore, the common difference is bounded. Okay, so what I just said is, this implies Hoff's theorem in the case of square-free moduli. Okay, so the square-free is just saying, okay, we're only going to use each prime once. If you don't want to do that, then it just makes the geometry a bit more complicated. But the whole proof will work fine with slightly more complicated calculations. Okay, so let's just work in the square-free to make make the ideas as clear as possible. Okay, so what was the proof? So Sk is just 1 up to Pk. Pk is the kth prime. The Chinese remainder theorem allows you to map progressions into hyperplanes. Right? Just saying that each number in ZQ whatever is equivalent to something in, so ZQ is the same as ZP1 cross ZP2 cross dot dot dot, just like we did in the very first slide. And then it just tells you that there's a modulus, there's a hyperplane, there's an arithmetic progression whose common difference is only divisible by the first C primes. So it's at most the product of the first C primes. So it's bounded. Okay. And also, so notice that, so we only needed Sk was bigger than 4K for large K. Pk is actually, so in the application, SKSI is about K log K. So it's in a sense quite a lot stronger. And it's moreover not far from best possible because you can't improve this 4 below 1. There exists a sequence of sort of sizes that's asymptotically equal to K, such that the theorem fails. So for every C, there's an N and a bad collection of hyperplanes. So non-parallel hyperplanes covering the world that does not have this property. Okay, and the proof is actually very simple. You just cover greedily. So this fits in with this intuition, this Philosetta Ford-Cunningham Pomerance U theorem, this 1 minus 1 over D. So you can always cover 1 over D proportion in each step, and that's basically all you do here. You just sort of cut out the proportion you can hope for, a 1/d proportion at each step. And if your SKs are growing not quite as fast as K, then this works. Then you can cover everything without using any small moduli. Okay, so I don't expect you to be able to see why this is true, but I just want to say that it's not difficult to prove. So if you just try to cover greedily and work out what it gives you, then it gives you roughly something a little bit less than K. Okay, so we have a geometric or combinatorial version of this of Hopf's theorem. I'm going to try and prove it. Okay, so what is the distortion method, the Hopf's distortion method? So we've got
just a small question here. It doesn't really matter this nature of SK, meaning SK doesn't have to have prime size or
no, not at all.
Anything,
yeah.
so it doesn't really matter.
Nothing to do with primes. Yeah, exactly. So it's not really a theorem about primes. Well, I mean, the primes tell you how to translate between arithmetic progressions and hyperplanes.
So this is
really this is the combinatorial thing that's going on behind the problem.
Okay.
Right. So how are we going to do this? We're going to reveal the hyperplanes in rounds. So these n rounds correspond to S1 to Sn. And we define these distorting probability measures. So the first one, P0, is just uniform. And then it's going to get gradually more and more distorted as time goes on. Right? And the kth measure, so in step K, we'll reveal the arithmetic progressions, the hyperplanes, whose maximal fixed element is K. Okay, so we've already revealed everything up to K minus 1. In step K, we pick everyone with max fixed element K. I'll show you a picture of this in a minute. And we'd like to do it so that we don't cover too much. Okay. We'd also like some other properties. We don't want to mess up the measure of the sets that we've covered already in the earlier rounds. We'd sort of like that to stay constant. And we don't want to distort things too much. So we want to try to just distort things subtly to try and push the measure onto the uncovered set. So the way that Hopf does this is, right, it's just to take the things that are covered and set their measure to be 0, and then sort of smear out. So now you've got some extra measure. So now your extra measure, sort of divide it in some way uniformly on what's left. But taking care not to change the measure of something that only depends on the earlier rounds. So so he does something like this. We do something that's a little bit different, and it makes life much simpler. So let me show you a picture. So here's the picture you should bear in mind. So on the bottom, the x-axis, we have qk minus 1. So that's all the world revealed in the first k minus 1 rounds. And then the kth step, we're sort of revealing this extra dimension, which is sk, the extra dimension of our sort of hypercube, or high dimensional cuboid. And so there's some things that have been removed so far, and they look like these columns. Right? If you've removed a point of qk minus 1, you've removed an entire column. And if you haven't removed a point of qk minus 1, you haven't removed anything of the column. So what survived is entire columns, because so far we've totally been working in the world qk minus 1. Okay, because all of the fixed elements so far were in 1 up to k minus 1, and the rest was just free. So there was you didn't even see those dimensions. But now we see them, and so the things that we remove look like subsets of rows of this rectangle, this picture. And I've drawn this because so I apologize for this picture. because I can't draw things in high dimensions or even 3 dimensions, you should think of these black dots as being a sub-hyperplane of this, this row. So I've drawn it as an arithmetic progression, but really it's a hyperplane. So it's some hyperplane in this k-1 dimensional world, which is this slice of this picture. Okay, and we're removing the steps of several of these things, and you can remove more than one from the same row, but anyway, so you can remove lots of stuff. Okay. So then what do we want to say? We want to say, okay, and then in the next step, we're going to sort of add an extra dimension, and all of the gray stuff, or the gray or black stuff will become gray in the next step. Okay. And we've got a measure on qk-1. We want to extend to a measure on qk. So a measure on the x-axis, we want to extend to a measure on the whole space. Okay, so here's the idea. So this perhaps will look a tiny bit technical, but really it's quite simple. So alpha k of x is just a proportion of the fiber x that we remove in each step. So x is going to be a point of our x-axis, qk-1. Alpha k, so if you look at one of these columns, you want to look at the proportion of the column that's removed in this step. Okay, so some of it's 0, some of them get 1 removed. Okay, perhaps in real life, some get many removed. Okay, that's your alpha k. It's the proportion of the column that gets removed, the column corresponding to x. Okay, get covered in that step. Right, so it's just the proportion of this fiber. The fiber is the column that is covered in round k. Okay, and so fixing some delta. If you remove very little of a column, then let's just 0 it out and then increase the measure proportionally on the rest of the fiber, the rest of the column. So if there's a column where you only remove a small amount, just put it to be, fix it to be 0 and redistribute the measure on the rest uniformly. If you remove a lot of a column, then we don't want to do that because that will distort the measure too much. So then we just cap the distortion by not setting the measure to be 0 on the covered set. We just increase the rest by this factor 1/1 minus delta and decrease the measure on the covered part. Okay, so if you remove a small amount of a fiber, just throw it out. If you remove a lot, then just adjust things by the amount that you're allowed to. Okay, and the point is that you never change the measure of any point by too much. Okay, so that's all the preliminaries. We're ready for.
So you don't increase the measure by much. So you decrease a lot for this.
Yeah, you're allowed to decrease a lot, but you never increase it too much.
And everything that happens on a single fiber of a fixed point in QK.
Yeah, so we do this on each fiber individually, exactly.
Okay.
On each fiber individually. Exactly. Right. Okay. So here's the key lemma, and the proof is almost unbelievably simple. So for any collection of hyperplanes, if we have this bound on the sum of the second moments of these alphas, then we know we don't cover. So here's the proof. So a very simple calculation is just say 4 or 5 incredibly simple lines. The most complicated line is this inequality, this very high-tech inequality I stated. Max of a minus b and 0 is the most a squared over 4b. The rest is literally just plug in the definitions and see what you get. Gives this inequality. Okay, you just plug in the definitions, use this super simple inequality. You can bound the measure. So bk is the set that's covered in step k. So this is the measure of this set in the kth measure is bounded by the second moment in the k minus first measure of the amount that you remove. Alpha k of x is the proportion of the fiber of x that you remove in step k. Okay. So just to unravel the notation, so really nothing happened here. We just wrote out the definition of the measure and used this simple inequality. But now we're done, because by the way we chose our measure, the Pn measure of bk is the same as the pk measure of bk, because we never changed the measure afterwards. Because on each fiber, we keep the measure the same. We just redistribute on a fiber. So if the assumed inequality holds, then the total distorted measure you removed at the end is less than 1. If the total measure you removed is less than 1, then you don't cover. Right? Oh.
So Rob, can you remind? So alpha k is what was covered on step k exactly.
The proportion that's covered in step k on the fiber of x.
And the pk of so bk is.
We're averaging over x, so we're averaging over the choice of x in the k-1 measure. So there's a k-1 measure on qk minus 1 that gives you a random x. So averaged over your choice of x in the measure of the previous step, the square of the proportion you remove, if that's small, then you don't cover. And
pk, so again, so bk is what was covered on the case.
pk is what's covered in step k.
Case step, right? Okay.
Exactly.
Okay, and then this is where you use this inequality, this a squared over 4b. So a is this alpha k and b is what, delta?
Yeah, something like that. Yeah, probably delta.
Okay.
Yeah, exactly. Yeah, because you started with you take away this this delta at most. Exactly. Right. Okay. Right. So in this slide, I mean, almost nothing happened, but this is really the sort of the key. And now we just have to calculate these second moments. We just have to bound the second moment. We've reduced the problem to bounding the second moment. Right. So all we have to do is bound the second moment of the amount that you remove with respect to this measure. And that turns out actually to be very easy. So we prove this bound, which basically says that the second moment is like squared times some error term. And the error term is small as long as this 3 over 1 minus delta size of Sj is what, smaller than 1 over k, basically. Or 1 over j, maybe. Right? So as long as Sj is going up sort of fast enough that this error term is small, then the second moment is small.
So this is where you use your
prove
condition,
this,
at least for k, right?
Yes, exactly. So yeah, we're going to use this. Well, I mean, not in this lemma, but afterwards. Yeah. Right. So we do. So a simple induction gives you this bound. So what's the induction? You just either k is a fixed element or it's not. If it's not, then you apply induction hypothesis. If it is, then you might lose a factor of 1 over 1 minus delta, because that's the maximum distortion you're allowed. Right. So this induction is using again the fact you don't change the measure in one step. That's the case where k is not a fixed element, and if k is a fixed element, you don't increase by more than 1 over 1 minus delta. Okay. So this slightly subtle thing of shifting the measure around but not too much gives this bound. And then it's again super easy. It's just a few lines. And now just apply this to pairs of sets, so pairs of hyperplanes, sum over all choices, and it gives the bound above. Okay, and the 3 comes from all the different ways in which you can take two sets whose union is a different set. Right, so you end up with a 3 to the size of the set. So again, this is just, it's a page of calculation, but it's very, very simple. How would you bound the second moment? You sum over all pairs of hyperplanes of the probability that they're at the intersection or whatever, and then you just apply this bound and see what you get, and you get this. Okay, so there's nothing interesting here at all. It's just how would you bound a second moment? You'd write out what it is, and that's it. Okay? And what we've used is that we didn't distort the measure too much to get this one minus delta. Okay, and now we're done. So let's just put it together. So I've stated here a slightly stronger version with the 4 replaced by a 3 plus epsilon. Okay, otherwise the same. So what do you get? So right, so we want to bound this. So from the key lemma, we want to bound this 1 over 4 delta, 1 minus delta, sum of the expectation of alpha squared. So what is that at most? By the bound that we just proved, it is, well, if you just plug in what you get, so sk is at least 3 plus times k, so sj is at least 3 plus epsilon times, is small compared with epsilon, then 1 plus 1 over j. Give some small error term. And okay, 1 over sk squared, we replace that by 1 k to the minus 1 plus epsilon, right? Because actually there's some error term. And this is summable because epsilon is bigger than 0. So this condition that sk is bigger than 3 plus epsilon times k is exactly to make this thing summable. Okay. Okay, and so C is sufficiently large, this is less than 1. And if C is for sets which are, what am I saying? Yeah, if there are no hyperplanes whose fixed set is in 1 up to C, then in the first C rounds, nothing happens. Because we only reveal things which are contained in the first, in step K, things that are contained in the first K elements. So nothing happens with the first C steps, and afterwards you gain this, this k to the minus 1 plus epsilon. And that's it. That's the entire proof. So it took a little bit of setting up, but once you have this, distortion definition, then the proof is sort of almost shockingly simple. So what it needs is, so we need to be in this high dimensional world, which, okay, we're often in this high dimensional world, but you need the set sk to be growing, at least linearly. And right, so it's perhaps slightly rarer to find an application where this is happening. So for other applications of this, well, we need to think of cases where your sets are growing as your dimension grows. So, I mean, I don't, yeah. If anyone has any ideas, then or problems they're thinking about, which in which that's the setting, then this might be a technique that's worth trying. Right. Okay. Sorry. So just a couple more comments on this. So this implies Hoff's theorem for square free moduli. Just set sk to be 1 to pk. It also gives the full theorem, but with slightly more complicated calculations. And if you want to get a good constant, you have to try quite a lot harder. But one nice thing about the method is you don't have to use the same delta at each step. So in each step you can use a different delta k, and if you optimize things cleverly and carefully, then you can push this constant down to something a bit more reasonable, so something less than 1 million. So this took some computer power, mostly by Paul. So Paul used quite a lot of cleverness and brute force to push this down as I guess as far as it can go. Right, so to finish, spend just 5 minutes maybe on this question. So this was really the question that got us going in the first place, this problem about the density of the uncovered set. And it motivated this modification of Hoff's method. So they have this lovely theorem about the uncovered set, but also this lovely question that I mentioned earlier. So is it true that if the sum of the reciprocals is bounded, then you miss a constant proportion? And we spent quite a lot of time trying to prove this was true. It seemed very, I mean, so natural that it had to be true, but actually it turns out to be false in the following very strong sense. So it's false even with c equals 1. So there exists a collection who cannot possibly cover, because the sum of 1 over d is less than 1, and the density of it, but they cover almost everything, and the moduli are all as large as you like. So almost covering really is different from covering. So you can almost cover as almost perfectly efficiently with large minimum moduli. I think it was very surprising. I was very surprised. So let me tell you the construction. It's very simple and rather nice. So you take a bunch of sets of primes, and you define your Qi to be the product of all the primes you've seen so far in the first I steps. And then the next step, you take your, so in the ith step, you take your differences to be each prime you have times all of the primes in the earlier steps. And with these differences, you just choose them greedily. So you just choose to cover as much as you can each step. And it turns out that's enough. To choose the primes is that sum of 1 over p diverges. So this allows you to choose very large primes in the next step that add up to basically what you want and independent of the previous ones. So basically you're sort of going into this subworld. Now, because of this product with Qi minus 1, you're only covering new things. So you don't get this orthogonality is what kills you. Or well, you might think the answer to the question was yes, was because you think that these things are basically orthogonal. And by going to this subworld of multiplying by Qi minus 1, again, this looks a bit like a frame, right? So this is all sort of connected to this counting problem. Even though the proof of the counting problem is very different, then really this sort of geometric way of thinking about it is very useful. This sort of frame way of thinking about it is very useful. Okay. So it takes maybe a sort of a page and a half to actually check the details, but the construction is really very simple. Okay, so this was, unfortunately, the answer was no. So this was not, the sum of the reciprocals is not the right thing. So what is the right thing? Well, it turns out the right thing is just, if you do something a little bit more complicated, gives you a little bit more strength, then something essentially, then the answer becomes yes. So replace this 1 over d by chi of d over d, where chi of d is this multiplicative function that instead of being 1 for each prime, it's 1 plus some polylog p over p. So if you just penalize things a little bit more strongly, then you can show the density of the uncovered set is positive and almost optimal. So we don't get the e to the minus c you might hope for, but e to the minus 4c. And this 4 is related to the 4 in the earlier theorem. So we're losing a little bit. Right, so this was actually the main theorem we were proving, which then led to this simpler proof of Hoff's theorem. So the proof of this, it looks basically like the proof that I showed you. It's been more the details are more complicated, but there aren't any really important extra ideas. So perhaps the main ideas are the ones that I showed you. And also a similar but slightly more complicated construction to the one I just showed you shows that really this 1 plus polylog over p is close to sharp. So it will be false not just with 1, but even with 1 plus constant over p, then the conclusion is false. So you can't force the density to be positive by taking something less than 1 plus something going to infinity over p. So again, this 4 is again, yeah, so all of these 4s are related. So final slide. So there are some other consequences of the method. So like I said, the method is very flexible. You can choose these delta k's as you like, and it allows you to prove lots of things about covering systems. So this conjecture of Schinzel I mentioned earlier also follows from an adaptation of the method. So you need some simple lemmas about antichains basically, and then you just run this sieve and it gives you what you want. This other problem, the Erdős selfish problem, which I mentioned, is stronger, so more difficult to prove than Schinzel conjecture. So Hoff and Nielsen used Hoff's method to show that, they didn't quite manage to show that you have to have an even number, but they had to show that either you have an even number or a multiple of 3. This disproved the stronger version conjectured by Erdős in a strong form. And it looks like you're almost there, right? You've got either a multiple of 2 or a multiple of 3, but actually things get quite a lot harder to getting rid of 3. So they had to work pretty hard to get this result. Our variant of the sieve gives this almost instantly in just a few lines. With some more work, we can get this slight strengthening. So not just, okay, either you have an even number or not just a multiple of 3, but a multiple of either 9 or a multiple of 3 and a multiple of 5. Slight strengthening. But this seems to be the limit, unfortunately, of our method as well. So things sort of get exponentially harder as you try and push further into this. With quite a lot more work, we managed to prove it if you restrict to square free. So this takes quite a bit more sort of case analysis and computational power and things like that. But it seems that our method is not strong enough to solve the Erdős selfish problem completely. So this is perhaps the main open problem. But for me, the main open problem seems to be try to use this apparently very powerful and flexible method in other settings. It really seems like it should be possible, but yeah, I can't see how to do it at all. Anyway, thanks for your attention.
Thank you very much, Rob. So let's applaud maybe. It was very interesting. So questions from the audience?
So I just wondered that what is the most interesting unsolved question after that? Sorry, I didn't hear. What is the most interesting unsolved question that remained unsolved after? Because at the end,
the most famous unsolved problem is, yes, the most famous is Erdős selfridge, but somehow I don't feel like it's the most. I find it hard to get really excited about it. It seems to me that understanding this geometric setting properly might be more interesting. And also there are lots of sort of natural extensions and questions which we haven't really explored at all. Why are we working in this particular setting?
Rob, you froze.
Oh, sorry. Yeah.
So you internet.
You disappeared for a minute.
And the most exciting question, like what is the best problem to work on, you suddenly disappear.
Yeah, right. So I would like to have a better answer for this. There are lots of questions.
We didn't hear it.
It's not. sorry. I would like. It's a very good question that I would like to have a better answer for. I don't have a very good answer. That there are lots of questions that have been asked. It isn't really obvious to me whether these are the correct things to push on. It seems to me that the most interesting thing about this is a method that doesn't look like anything else I've seen elsewhere. This distortion method of Hoff. I don't know if, I mean, you're more experienced than me. Perhaps you've seen something that looks something like it somewhere else. But it really looks to me like something new and different, and I don't know how to use it in other settings. And this setting that we're in, it's extremely combinatorial, right? That we're this geometric world, and lots of combinatorial problems look like this. Should be translatable into something that looks like this, or even things that, right? I mean, there's lots of things that are being proved with random processes at the moment. This is like a way of attacking a deterministic process with random methods. So I would like to see some application, just maybe in a totally different setting, where you have some kind of process that you want to follow, and you feel like it should look quasi-random, but it's not random, it's deterministic. Right? It allows you to treat a deterministic process like a random process in a certain sense. And it's because, I guess, of the orthogonality, right? Because these primes are orthogonal to each other, then when these arithmetic progressions, these hyperplanes hit it, I mean, the hyperplanes are sort of orthogonal to each other, right? I mean, they essentially are orthogonal to each other. But I've been looking and trying and failing. But I think it's not something that I'm very good at, spotting these kind of applications. I think there are some people who are extremely good at sort of finding problems that you can apply a method to. So I hope that that some of those people take an interest in this. I mean,
so speaking of this method, so Rob, speaking more of this of the method, so can you give a bit more intuition on why this kind of iterative thing helps? So why does it help to do it gradually somehow, and not
so my intuition for this is, yeah. So we're adjusting. So it's a sort of dependent random choice that we're choosing the measure depending on what we've seen so far. So just like in random processes, like the random greedy processes in graphs, then you want to break it up into sort of as small pieces as possible. And when you break into small pieces, then you can control each piece. You have more ability to control each piece. And so I mean, Hoff wanted to do it in a bounded number of steps. So because he was losing quite a lot in each step, and so he didn't want an unbounded number of steps. I think so. It's because things would fly out of control. But actually doing something in the opposite extreme, doing it sort of as tiny steps as possible. I mean, in lots of cases, this has made life easier. Right? There's been lots of results using sort of nibbles.
Yeah, so it's like a nibble
small steps as possible. Right, it's like a nibble, exactly. I mean, I mean, like the sunflowers magic that that they nibble away at things and control them. I mean, there it's right again. It's essentially random, or at least in the canonical Lie conjecture application. Right, there seems to be a different way to do a nibble. And a way to do a nibble in a totally deterministic setting.
Okay. That's ways to think about it. So someone asked about availability of the results. I imagine that all of them are.
Yeah, sorry. My intuition is that this technique should be useful in lots of other settings. It should be sort of an important tool in the probabilistic method.
Okay.
Sort of this distortion of a probability space in order to focus on the thing. I mean, perhaps another covering problems are a natural place to look first.
Yeah.
There's many covering problems that I'm not really sufficiently familiar with all of them to know where to start. But perhaps people who have worked on covering in other settings would be able to spot something.
Okay, that's very interesting. So someone asked, Sergei Tarasov asked about the availability of the papers. I guess all of them are on archive. Even the
everything's
results.
on archive.
2020 plus, it means that it just hasn't been published, I guess. Right?
Yeah, right. So one of them has been accepted. Two of them have been submitted for a while. There's also the short proof that I presented is in the Semirady birthday issue, but maybe we haven't put it on archive yet. So maybe I should put that on archive. Yeah. So there's a short sort of eight page version of Hoff. Which
I think it has appeared already.
It's already appeared. Okay, so it should be available somewhere.
Yeah, Acta Hungarica.
Right.
Yeah.
But yeah, everything's on the three big papers, sort of each about 30 pages or something, are on archive.
Great.
Yeah, I mean the counting also seems interesting to me, but it's perhaps getting the structure properly is a bit technical. But I think that this, I mean, Erdős always asked the simplest version of the question, right? The one that we've got it down to its essence. But now that we sort of understand to some degree what these covering systems look like, there should be lots of other sort of slightly more complicated settings, more general settings in which one could try to work. But there's no particular reason we should necessarily be sticking to, I don't know, arithmetic progressions or to the sorry David Conlon asked a nice question in when I talked about this in Oxford maybe about other groups. Right, so we're working in Z, but why shouldn't we work in any other group and try and cover any other group? And I haven't thought about it at all, but I believe that there are some nice conjectures or open problems out there. Which I mean, I've no idea if the same sort of things work or not. Right. There are also questions about covering with, you want to cover not just once, you want to cover several times. There are lots of the Erdős questions that I've completely forgotten that we thought about and got stuck. They seem to be sort of different in some fundamental way. So if you want to cover not just once, you want to cover twice or 10 times or something, then it seems to be somewhat different. I think in Ben Green's Ben Green has a nice collection of open problems in number theory. I think some of them may be stated of covering and sieving problems. So lots of these things they don't look very combinatorial at first, but actually they're really very combinatorial questions.
Okay, great. It's there is a lot of things to look at, say. So thanks a lot. I guess there are no more questions. So thanks a lot, Rob, and
thank you very much.
Wonderful talk. Hope to see you sometime reasonably soon offline. That would be really great.
Yeah, fingers crossed.